So in the previous module, we have introduced this notion of perfect information extensive form game, and we have seen that this game is more appropriate to represent certain kind of games which are not getting over in one round. So this is more appropriate for representing games which are multi-stage games. Different players are taking turns one after another, and then they are playing. So, and we have also reduced a PIEFG into a normal form game, and we saw that there are some difficulties when we are using the equilibrium notions of normal form games. Sometimes the pure strategy Nash equilibrium, which is the most remarkable solution concept for normal form games, they are not really meaningful in the context of extensive form games. So when we are discussing this kind of games, not only in terms of the representation, we also need a different equilibrium definition. So in this module, we are going to discuss about some equilibrium guarantees which are appropriate for PIEFGs. So let us look at another example. It's a very similar example that we discussed last time. In this case, there are three stages of the game. In the first stage, player 1 plays. And in the first stage this player has two actions available, so A and B. And once it plays that one of these actions, it's player 2's turn who wants to move. So if player 2, so if the graph essentially the game tree actually shows that what are the different possibilities, the actions available if player 1 plays A and then player 2 plays C or D, and correspondingly the game ends. So in this case the game ends in this branch of the game tree. In the other branch of the game tree, it does not end right away. So if player E plays, player 2 plays the action E in the second round, then it ends. Otherwise, player 1 gets another chance to play, and at that point, the player has two options, G or H. So, so how should we proceed in understanding what will be a reasonable outcome? So you can see the way we have defined the strategies for player 1 in extensive form games is the complete contingency plan. So player 1 in this case can play in the first round, or in this branch here in the second round, in the third round. Now, therefore, the strategies could be AG, so which means that player 1 is playing A in the first round and G in the third round, AH similarly, and BG or BH. So it gives the complete plan. If at any history, any non-terminal history of this game, the player 1, whatever it is going to play, is already spelled out in this strategy. Similarly, you can write down the strategies for player 2, C, CF, D, DF. Now you can transform this game into the normal form game and write down all the possibilities, all the actions and their corresponding utilities for these players, and you can find out the pure strategy Nash equilibrium. So let me give you the pure strategy Nash equilibrium in this case. So they are AGCF, AHCF, and BHCE. Now, the moment you look at this game, the pure strategy Nash equilibrium of this game, there are certain things that you can see immediately in the light of what we have discussed in the previous module. So there are some non-credible threads here which is going around. So look at this two pure strategy Nash equilibrium, AHCF and BHCE. It is saying that in the third round, player 1 is going to play H. Now, when does player 1 gets a chance to play the third round game? Only at this history, right? Now, in this context, if you just imagine player 1 and assuming that player 1 is a rational player, if the game ever reaches this history, here, will the player ever play H over G? Because player 1 gets utility 2 here if he plays G, and it gets utility 1. So even though it's a pure strategy Nash equilibrium, this threat is quite non-credible. Player 2 also knows that if that game ever ends in ever comes to this non-terminal history, player 1 being rational will never choose H. So therefore, this 2 equilibrium, even though it is giving some guarantees in terms of Nash equilibrium, it is never a credible threat. While AGCF is indeed a credible threat, because if it reaches here, then of course player 1 gains by choosing G and H. So that's the point that we want to capture in this game, the rational outcomes of this game in a reasonable way. So, and clearly the pure strategy Nash equilibrium is unable to capture that thing. So let us look at what are the possibilities and the notion of this playing the game at any history is already giving us some hint that how we can define rationality. So the rational outcome in this perfect information extensive form game will be better if you consider the history and ensure the utility maximization at every history, and that is exactly the notion of subgame. So what is a subgame? So it is a game that is rooted at any intermediate vertex. So let me do it in a little formal way. So the subgame of a PIEFGG rooted at a history H is the restriction of the same game to the descendants of H. So let us just try to understand that. So let me just erase this part. So if you are looking at any history, so what is a history? So in this context, the history, so if you are calling this node as the history, then H is B and F. So this is the sequence of actions that the other two players have played in order to reach this node in the game tree. So the subgame rooted at this H at this history is just this part of the game. You can see that this is also a perfect information extensive form game. Similarly, if you are at the history of B, then you can consider that this part is the subgame. Similarly, there is another subgame here, and of course the whole tree is of course the trivial subgame of itself. So that way you can define various subgames, and so subgame can also be defined at the terminal nodes, but that does not really make much sense. So we'll only be considering the subgames that are rooted at non-terminal histories. Now we define as the set of subgames of G to be the collection of all the subgames at some history of G. This will include both the terminal and non-terminal histories. Now the moment we have defined a subgame, it automatically gives you the rationality concept, and that is defined with respect to the subgame perfection. So it should be a best response for the player who is playing at that subgame, and that should happen for every subgame of this game. So let us formally define, and then we try to understand how it is done. So we call subgame perfect Nash equilibrium of a perfect information extensive form game G, and this is all strategy profiles S. So this is the strategy profile for all the players. Every player has picked some strategies, and such that for any subgame G prime of G, so you reduce the game, you look at any subgame of the original game, then you can also restrict the strategies of those players to that subgame, and that restriction of S to G prime must be a PSNE of that restricted game, of that subgame G prime, right? So in the previous context, if you just think of this subgame here, this subgame, then clearly this playing H. So you can think of that if this was the strategy. So let's say this is S1 and this is S2. Then the restriction of S1 comma S2 to this subgame, so let's call this subgame to be something, some gamma, say gamma 1. So that restriction will just give you the strategy for player 1, which is H. And that is clearly not a pure strategy Nash equilibrium, because player 1 clearly gains by playing G. So therefore, this definition of subgame perfect Nash equilibrium rules out these two possibilities, AHCF and BHCE, because in both these cases, at least there exists some subgame where the restriction of the original strategy to that subgame is not a pure strategy Nash equilibrium. Whatever is remaining, you can check that this is actually a pure strategy Nash equilibrium. You consider not only gamma 1, all possible other subgames, and you can see that the strategies that has been played by these players is actually the pure strategy Nash equilibrium of that subgame. So this example essentially talks about that a little more formally. So you have this AHCF, BHCE, and AGCF, and the thing that we have just discussed, you can find out that you can eliminate these two strategy profiles, because they are not PSNEs at every subgame of this game. Now the very natural question is how to compute this subgame perfect Nash equilibrium. This sounds like a really interesting idea, a new concept, but then again we have to compute that carefully. And by the definition of subgame perfection, you can already start thinking about how this computation should start. Imagine that we only have finite games, and therefore you don't really have to worry about infinite branches of this tree. So how should we actually start computing this? And the most natural way is to start from the leaf node and start. So once you have found out at the leaf node, the node which is just above the leaf, let's say here or here, you can actually find out what is the pure strategy Nash equilibrium in that history of the game, and then you kind of recursively find out what should be the best response of the player in the previous stage of the game, previous history of the game. And this procedure is actually called backward induction. It's very simple an algorithm. So let me just go over the pseudocode, which will also essentially will capture formally the things that we have discussed. So let me just show you the example first and then give the pseudocode. So if you start from this leaf node, what should be the action of player 1 at this subgame? Clearly G, so you can write that as the strategy for player 1. Now given that player 1 has played G, so what should be the action of player 2? If that game ever reaches this history, what should player 2 do? So it sees that player 1 is going to play G, therefore player 2 is going to get a payoff of 10. While if player 2 plays E, it is going to get a utility of 5. So clearly this is larger, so therefore it should pick F. Player 2 should pick F. Similarly, you can find out what player 2 should play in this part of in this subtree at this history. So clearly player 2 gains here, so it should pick C. And now at the node, at the root node, where player 1 is thinking about what to play, so it already knows, it has already solved the subgames of all the subtrees starting from that node. So it knows that if it plays A, the player 2 will play C, and agent 1 will get a utility of 3. If it plays B, player 2 will play F, and then player 1 should play G again, and that gives a utility of 2. So clearly this is larger, so therefore it should pick A. So therefore you can see that AG for player 1 and CF is the pure strategy Nash equilibrium using this principle of backward induction. And quite clearly, we can formally show that this is a pure strategy Nash equilibrium for the whole game. If you reduce this PIEFG, we have already seen this, but it has to happen all the time because it's a pure strategy Nash equilibrium at every subgame. So if you put the whole game together, then it should also be a pure strategy Nash equilibrium. But this is not so obvious. It needs a little bit of formal proof. So let me end this module by giving you the pseudocode for this backward induction algorithm. It's actually pretty simple. It is starting with any given history and then recursively calling itself. If that is a terminal node, you are going to return the utility at that history for both these players, and let's say the action. So this function is going to return you the utility and the actions of the players, or action of the player at that history. That is better to define. So of course, if you are at a terminal node, you have no actions left, so therefore you don't return anything or return null. For if it is not a null node, not a terminal node, then you start with defining this best utility to be a very large negative number. So note that this is the best utility for the player who is playing at that history. And now you run a loop for all the actions that are available at that history. Append that action to this history and call the backward induction function again. So this is very much similar to a dynamic programming. So once you find all the solutions, you can actually memorize and make this more efficient in terms of space. But here we are just giving the idea. So the history and the action, so you put them together. So this is the new history, and whatever you get back from the backward induction, take the utility part here. So this can be interpreted as just the utility part. The moment you get this, you check whether this is greater than the best utility that you have seen so far. If it is so, then you replace the best utility and also replace the best action. And finally, after you have run through this for loop completely, then you return the values of the best utility and the best action. Very simple. It uses this recursive call and finds out. So essentially you are going to the depth of the tree, finding out what is the best action and the utility for that player, and then coming up towards the top, which is the backward induction algorithm.